Carlos used anonymous projections to control the query and to limit the results. Controlling the query with a more carefully crafted link statement helped him with database performance. It gave him control over what happens in the database so that he could coax EF into producing well-performing SQL. Limiting the results, on the other hand, helped with network performance. He was able to cut down on the number of rows returned. And he was even able to eliminate some columns that didn't need to appear in the projection. There's one more benefit to using anonymous projections over entities, and that is improving runtime performance by eliminating change tracking. You see, EF can only apply change tracking to entities. Anonymous projections cannot be tracked, and therefore avoid that overhead. To get the most out of runtime performance, it's best to disable change tracking whenever you don't need it. And of course, the only time that you do need it is when you intend to make a change. And so a good practice is to always be aware of whether you are writing a query or a command. Vladimir Korokov, in addition to having an excellent course on encapsulating EF Core 6 usage, has published a must-see CQRS in practice course. In that course, he explains that command query responsibility segregation is the observation that code should have two distinct paths: commands that flow in toward the database and queries that flow back out toward the user. The decisions that you make along the query path don't necessarily apply to the command path, or vice versa. Change tracking is one of those decisions. It only makes sense for the command path. Now, a query might lead up to a command. In a web application, for example, a query might render a page that is then used to submit a command. But those query results become disconnected from the DB context. When the eventual command comes in, it will be served by a different DB context instance. If you separate your queries from your commands, then you can apply the appropriate patterns for each. Focusing just on the query path, we can see that a query will either select entities or projections. Carlos found that selecting projections gave him the control that he needed in order to optimize the query. But if he had selected entities, then he would have used the as-no-tracking method to minimize the runtime overhead. There's no reason to track changes if no changes are intended, and changes only happen along the command path. Establishing a good convention of separating commands from queries makes it easier to determine which patterns to apply. EF Core 6 introduces a new tool for improving runtime performance, specifically at startup. Compiled models reduce the time to first query. Rather than performing reflection and fluent configuration to understand the model at runtime, EF Core 6 can precompile it for faster initial load. Carlos will compile the model in continuous integration for downstream deployments. We saw Carlos set up CI previously, when he built the migration bundle into a Docker image. To compile the model, run .NET EF dbcontext optimize. Specify the project that configures the DB context for the target persistence model. In Carlos's case, the target persistence model is SQL Server, and that's configured in GloboTicket infrastructure. This command generates a set of code in the compiled models folder. It describes in detail each entity, property, and relationship inside of the model. This code will run a lot faster than the reflection that would otherwise need to take place. But of course, you'll need to run this code on startup, and the command tells you exactly how to do that. Add the line options.useModel to the addDBContext lambda. Now, the developer would need to remember to recompile the model every time they changed an entity. Carlos knows that his team is going to do that quite a lot. They'll even iterate on model changes inside of unit tests before even generating a migration. And so, he hatches a plan to automate this process. First, he wants developers to use the reflected model rather than the compiled one. This gives them the most flexibility, allowing them to quickly change the model without also remembering to run the tool. So he moves the use model into a condition that is only run on non-development builds. Development builds will still use reflection and fluent configurations. Next, he adds the dbcontext optimize step to continuous integration. He's using Azure DevOps build pipelines, so the steps for the CI build appear in the Azure Pipelines YAML file. Compiling the model will require 3 steps. This will first require that he installs the EF tools on the build agent. He does that with the .NET tool install global.NET EF. Next, he sets the environment variable for the admin connection string. This is necessary because he uses the environment variable to set up a design time DB context. Now, the DB context optimizer doesn't connect to the database, and that's why we don't need to specify a valid connection string. However, the design time DB context factory that Carlos created requires this environment variable. And finally, he calls .NET EF DB context optimize. This generates the compiled model before running the build step. And now every downstream environment will have an up-to-date compiled model, and developers don't need to remember to run the tool. Carlos has adopted a few best practices around performance. He begins by putting in query tags to identify poor-performing queries. That allows him to focus his efforts where they will yield the best results. And then he addresses database performance by favoring anonymous projections. This gives him the control to determine exactly what work to do in the database and what work to do in the application. And then to address network performance, he limits both the rows and the columns that are returned from a query. Using projections instead of entities allows him to turn a left join into a subselect and avoid bringing back the full entity to the application. And finally, he addresses runtime performance by disabling change tracking on queries and by building compiled models in the CI step. With these best practices in place, he can provide an optimized user experience without sacrificing developer productivity. Hello, and welcome back to EF Course 6 Best Practices. I'm Michael L. Perry. We've optimized performance of our EF Core applications while dealing with small result sets, and so now let's deliver large result sets using async streams. When thinking about performance, we focused on returning only the results that were necessary. Our first impulse should always be to return a smaller dataset, not a larger one. But most queries that we write are intended for human consumption. Web pages, mobile apps, and reports display a limited set of data to the user. You can usually improve the performance of these queries simply by returning only what the user sees. But when the data is intended for a machine, then we might need to return a lot of it. For example, exporting data from one system to import it into another is just going to require streaming a large set of data. There's really no way to avoid it. But fortunately, you can improve its performance. There are many dimensions to Entity Framework performance. We've already examined database, network, and runtime performance, so let's add 2 more to that mix: latency and scalability. Latency refers to the amount of time that a consumer of a service waits for results. One important metric of latency is the time to first byte, or TTFB. That's the amount of time that a consumer has to wait before they can even start processing the results. There's work to be done on both the producer and the consumer, but a lower time to first byte means that more of that work can be done in parallel. And then there's scalability. Scalability refers to the efficient use of resources as the load increases. If resources are not used efficiently, then more servers must be allocated to meet demands, increasing cost along the way. EF Core has features to address each of these issues, and now with .NET 6, it can even address them both at the same time. Let's see how. When you fetch the results of a query using toList async, you're telling EF Core to buffer or load the entire result set into memory. The application does not continue until the full dataset is loaded. And for large datasets, this leads to a long time to first byte. To improve latency, EF Core gives you the option of streaming the results instead. When you replace toList async with asEnumerable, EF Core will give you back the first row as soon as it's available. And then, as you go back for each additional row, it will fetch them one by one. This reduces latency, but it does not address scalability. EF Core offers a different set of features for that. Blocking methods, such as toList and first_default, hold up the current thread while waiting for results to come back from the database. Threads are expensive, even when they're not taking up CPU time to do their work. To be more efficient with threads, it's best practice to favor the asynchronous methods like toListAsync and first_default_async. These methods will relinquish the server thread until the results are ready. Fewer threads means that the same server can handle more load with the same amount of resources, and thus improve scalability. Now, if you wanted to improve both latency and scalability in the past, then your options had been limited. EF Core 3 introduced support for the iAsync enumerable type, and this type provides low latency by streaming rather than buffering the results. In addition, it also provides scalability by fetching each row without blocking the thread. Unfortunately, in .NET Core 3, that latency improvement did not make it to the consumer. ASP.NET would buffer the iAsync enumerable action result rather than stream it to the client. Now, that's been fixed in ASP.NET Core 6, and so we can now eliminate both blocking and buffering to improve latency and scalability. Carlos and his team have identified a problematic API. It returns a large amount of data, and the time to first byte is longer than they would expect. He finds that the API method loads the entire dataset, even though it's non-blocking. And so he first changes the query in order to stream the dataset. However, he does that in a way that is blocking. And then finally, he settles on a solution that's both non-blocking and streaming. The GloboTicket API has a feed endpoint that's used to download a feed of all of the shows. When he hits the API endpoint, the time to first byte is 1.6 seconds, which is much longer than he would expect. It should start downloading results as soon as it has the first row. And so he investigates, and finds the show's feed controller action. This controller action calls a service method that calls toListAsync. Being an async method, this is non-blocking, and so it's not going to tie up a server-side thread while it runs the database query. But even though it's non-blocking, this function does load all of the results into memory. And so he tries a different approach. Rather than returning a list of show info, he'll return an IEnumerable of show info. He'll do this by calling asEnumerable rather than toListAsync. AsEnumerable is not an async method, and so he has to remove the task, the await, and the async. And then, up in the controller, he does the same thing. And now he has a method that is no longer async, which means that it is blocking, but it's returning an IEnumerable, which means that it can stream. And then he runs the application to see what the result is. And when he hits the endpoint again, he finds that the time to first byte is much better. It takes just 45.88 milliseconds as opposed to 1.6 seconds. The important thing is that IEnumerable is able to return the first row as soon as it's available. But that's still not the ideal solution. You see, IEnumerable is not async, which means that it's going to block the server's thread as it fetches new rows. To solve that problem, Carlos decides to switch to iAsync enumerable. And that means he needs to call asAsync enumerable inside of the service method. And then he runs the application again to compare results. Using the iAsync enumerable, he's also able to achieve the very low time to first byte. In this case, 42 milliseconds, which is comparable to the earlier 45 milliseconds. But now he's confident that fetching the new row will not block the thread. He's able to return the feed while using fewer resources on the server side, which gives him a better chance at scalability.